Okay, so far we have seen the set membership problem has function, has table, and insert, delete, search operation. Now collision. Okay, already told there may be two elements going to the same place. How to handle that? We can make the table size bigger. That will reduce the probability of collision, but how much bigger? So before going to that, let's uh, see one practical phenomena we call birthday paradox. What is that birthday paradox? Birthday paradox means suppose there is a class of 30 students, and if I ask how many of you share the same birthday, okay, so there will be more than 50% probability that one pair share the same birthday. Okay, and this happens if there are 22 or 23 students, then it is already 50%, more than 50% probability. For 30, it will be higher probability. And if we have the class of more than 50, maybe 70 or 80, there will be 98 or 99% probability that uh, there is a collision. Okay. So now, how this birthday paradox is related with the hashing. If we plot the same scenario in the hash function or hash table, so it simply means that we have a set S of 30 elements, and we have a table of size 365. Then there is more than 50% probability of collision. Okay. So for 30 element, we are using such a long table of size 36, 365. Still there is a collision. And what is the function? But the function is, you can say, it is almost very near to random function. Okay. And still using that function, we have this type of process. So whatever the function you are using, uh, but the paradox assure us that there must be collision. There must be collision until unless table size is 5 times or 10 times bigger. Okay, there must be. But the 5 times or 10 times bigger means wastage of lot of memory. Especially if we are dealing with very large collection of gigantic table, and we are using hash for that, then we cannot afford so much memory. So how to handle collision? We have to find out some mechanism. Collision must be there, so we have to find out some mechanism to handle the collision. So the first known method for handling collision is chaining. Okay. This is very successful method for handling the collision. What we do in chaining, we basically this is our hash table. Okay. We are mapping elements. So what we do, we maintain different chain with each uh, position of the hash table. Let's say this size is m, and let's say there is some element. So we will say, okay, there is some element, and we will maintain a linked list sort of things, and inside the value, let's say k1 b1. K1 b1 is inserted there. Is fine. Now k2 b2 is inserted somewhere there. We will insert in this way k2 b2. Okay. K3 b3, let's say inserted here. Is fine. Now k4 b4, it's demanding the same position. There is a collision. So we are going to implement in this way. There will be k4 b4. So collision, all the colliding elements will be added in separate chain with the same position. Now the how search process will work. Suppose we are searching for some, these positions are empty, these positions are empty. Okay. Suppose we are searching for some element kx. Okay. So suppose we found kx somewhere in this slot. Okay. So we found that this slot is empty, so kx does not present. But if it's it is happened that kx is found here, so we'll start finding inside the chain until unless from the beginning to end we will look up this chain to find out the element. Okay. So kx may be found in this list. If it is found inside this list, then we will return, and if it is not found, then we will return the element not found. Okay. So this way we will search for the element. Now, will it increase complexity? Is it going to use lot of memory space? So there are many questions appear directly with this. So let's start with this complexity. Okay. So suppose we have inserted our set as n element, and we have inserted all the elements in this hash table with chaining. Okay, separate chain for every position. So how many total number of elements will be there inside the chain? What will be the sum of all the chain? That is going to be n elements. Okay. So these n elements, because there are n elements, so this chain, if we add the length of this chain, length of this chain, length of this chain, and length of all this chain, there will be total n number of elements. Okay, because there are n elements. So now, how many elements are present in each slot? There are m such slots, and n element is distributed over m such slot. Now we come to the question, what will be the size of m and n? Should we take m less than n? It may happen. If we take m less than n, it will work. But there will be chain length will get increased in this case. If we take m equal to n exactly, there will be probability of chain length. What will be the probability? Probability will be 1. Average chain length will be 1. But in worst case, if we does not have a good hash function, then some chain may get very longer and some other chain will become smaller. Okay. And if we take m little bit bigger than n, okay, not very much, almost this, or we can write this equal to, sorry, equal to order of n, means m is almost equal to n. Maybe m is little bit bigger or n is little bit bigger, that is fine. So we can handle these things with chain. Now suppose we are inserting lot of elements, and the chain lengths are growing. So what we will do? We can increase the size of the table. How to increase the size of the table? If we increase this, let's say m is replaced with 2m, what will happen? Should we keep lower block empty and all the chain in the upper block? No. We'll go for rehash with the table size m, 2m. Okay, we'll go for a rehash function with table size 2m. So what will be the complexity? This looks like very high complexity. What will be the complexity of that? Table doubling, it will be order of n, but we want the operation of the hash function insert, delete and search in constant time. But here insert will become order of n. Is it? No. It is not. We can simply compute amortized complexity, means how many times we are doubling the table. Are we going to doubling the table with each operation? No, not at all. We are doubling the table when n is bigger than, then only we are doubling the table. Okay, so how many times we are doubling? So let's start with the table of size 2, then we are doubling the table. When n is greater than 2, then we are doubling the table. Then at 4 we are doubling the table. At 8 we are doubling the table. At 16 we are doubling the table. At 32 we are doubling the table in this way. So how many times we are doubling the table? We are inserting n element and we are doubling the table. This is a geometric series. So we are doubling the table how many times? Let's say our final table size is 32. Okay, so we have made double in 16, in 8, in 4, in 2. Okay, so the final size is, so we can insert 16 element here. Okay, after 16, inserting 16 element, we will go for doubling the table. Before that, we have inserted 8 element. Before that, we have inserted 4 element. Before that, we have inserted 2 element. Okay. So, how many total operation and doubling the table? So, if we distribute this doubling table operation over, so total, if we sum all these things, it will become less than equal to 64. Okay. So, the 64 total number of operation we have performed, and our table size is 32. So cost of per operation is order of 2. Okay. Which is in the order notation. That is the beauty of order notation. We can write order of 1. Okay. So even if we are doubling the table, and that looks like a very costliest operation, but it will still give us the complexity of order of 1. Okay. So once we have doubling the table, so there will be associated concept of shrinking the table if we have deleted lot of elements. Okay, but in the reverse way we can do the shrinking, but we have to be little bit careful. How? Let's say we have 16 elements. Okay, so we have inserted one more element, 17 elements. We are going for table. Then we have deleted two elements, became 15. We'll go for shrink the table. Then again we have inserted two elements. So there will be lot of table doubling and table shrinking operation, and that will violate this constant time condition. It will make the complexity order of n. So we'll avoid that thing. For shrinking, we'll shrink the table if the deleted elements in less than 2n. Okay, means we are at 32. Okay, and our number of elements is less than 16, then we will sync the table. Not just 31 and we have synced the table. When it will come to 16, then we will sync the table. Again, when the table size is 16 and the number of elements is less than 8, then we will sync the table. Okay, in this way, this sync operation will work. And that will remove that possibility of the doubling and syncing in every operation. This is very interesting concept. And one more thing to say, this n by m is called the load factor. Okay, when the load factor is 1, we'll go for table level. We generally the preferred load factor is 0.52 m. Okay, that is the preferred load factor. And the chain length, average chain length, if we choose a good hash function, that will be 1 or 2. So that's all about the chaining method and the load factor table doubling. Okay, and the complexity of table doubling. So we have covered up to this 6. We will cover the next thing in the next lecture.